Hello, today we're going to look at topic 6.1, slope fields. This is our last topic in our unit that we're studying on differential equations. And so today we're going to focus on what we call slope fields. This is pretty much going to be part of your differential equation FRQ, and you might have some multiple choice questions that go right along with it. So basically what we're doing here, and it's in the first line where it says slope fields or direction fields. So these are little graphs of tangent lines that show the slopes at various points that are given. It's a graphical representation of a differential equation. It gives the picture. And so when we look at the slope field then and we solve, the picture looks like the general solution when we're doing that. And so I don't think that's any better, so we'll do this. Okay, and so the visualization of the parallel curves that solve the differential equation, and we're solving this without algebra. So that's what we're actually accomplishing when we look at the slope fields. So in this topic, we're probably going to find it showing up with our differential equation FRQ, but also possibly some multiple choice questions. So at the end of this lesson, I do have a code that is good for a practice of matching differential equations with their slope field. So you can find that on the teacher video note page, or you can combine ask, and that link is good for 2 weeks. So you can practice the part of this where you're making sure that you can match up graphs with their slope fields. So keep in mind that this picture, this slope field, is a slope field of tangent lines at each point on the grid, which is this part right here. And that tangent line is going to, at each point, is going to give us a picture of what the graph looks like. So on the AP exam, the slope fields can be maybe up to 2 points. And so you must draw the little marks for the tangent lines at each dot on the graph. Don't leave any dots unmarked. And it's not usually more than maybe 9, 10, 12 points. So the ones that we're doing today, like this one, are way bigger than you'll actually see on the exam. But I wanted to give you a field big enough that you could easily see what this is going to look like. So when they're grading this particular slope field, they're going to be looking for the horizontal tangent lines. They're going to be looking for where anything is undefined. They're going to be looking for positive slopes and negative slopes. Now, they're not going to pull out a protractor or a compass or anything and measure the exact angle. But basically, the general guideline is if it's a slope of 1, it should be at about a 45-degree angle. And then anything with a steeper slope should be bigger than that. Anything with a slider or smaller slope should be a little flatter than that. But they use kind of that 1 as, the mark. On multiple choice questions, you might be asked to identify the graph of a slope field. You might be asked to pick which one could be the slope field for the differential equation. So those are all possibilities to think about as we're moving through the lesson. All right, so to sketch the slope field, we're going to select ordered pairs. So the ordered pair for this point is what I'm talking about. And I have provided you with a table here to write everything down that you needed to figure out. So we have a column for the X point, a column for the Y coordinate of that point, and a column for the slope. And so remember that a derivative equation is a slope generator. So this slope generator right here is going to generate all the slopes at all the points on the slope field. Okay, we're going to substitute the original pairs into the differential equation and then compute the slope. And so I gave you a place here to write it. You don't have to use the table. I think if it's a very complicated differential equation, setting up a table of values would be helpful to keep you from making common mistakes. But if it's a small one, like the ones we're doing right here, then you probably could maybe just do and crunch the numbers without needing to write it in a formal table. And then we're going to construct short line segments on each dot to approximate the slope of the tangent line or the solutions at those points, right? So that's what the tangent line is. So once we do that, then for a particular solution, that general solution is going to be, the picture is going to look like the general solution. And then once we're given a point, we're going to put it into the differential equation and, or sorry, into the slope field and then sketch what the graph would look like. So we sketch the curve using an initial condition, and we use the lines of the tangent lines to guide the way we graph. So that's the long and the short of the process. We're going to do some practice to make sure everybody's good to go on the first part, and then we have a few FRQs that we're going to practice today. All right, so if this is my differential equation, what type of function would have a derivative that is linear? Right, so if I've taken the derivative and now it's linear, what would this have had to look like before I took the derivative? And hopefully, as you think through that and realize if it was a line, then I decreased the power when I took the derivative. So if I work my way backwards, then I might want to know that my y is quadratic. All right, so just working backwards, quadratic. Okay, I think you can see it. Okay, so I can keep that in mind. If I wanted to go ahead and actually calculate this equation to prove that, I could separate my variables. And if I separate my variables, I'd say dy equals x plus 1 dx, and then I can integrate both sides at the same time. And then I'm going to have y on the left-hand side equals, add 1, so 1/2 x squared plus the x when I do the 1, and then I have plus c. And as you can see right here, what did I get when I actually did the differential process? I got a quadratic function. Okay, so that was just me proving to you that this was in fact quadratic to begin with. But we don't need to necessarily solve the differential equation to be able to look at the picture and see what's going on. So we are going to start by picking some points on the graph and then filling in our slope field. So I'm just going to pick some points. Let's pick the point -1, 0. So that means I'm putting x in from my -1 into my slope generator, and my y would be 0. So, well, there's no y to plug in here. So I'm really just plugging in my x. So what is -x plus 1? The slope then is going to be 0. Okay, so then I go to the point, excuse me, -1, 0, which is right here, and I'm going to draw a horizontal tangent line. So just a little smidgen of a graph that represents the slope of the tangent line at that point. All right, how about the point 0, -1? So if I'm here at 0, and, oh, not -1, let's do +1. Let's do the positives first. All right, how about 0, +1? So 0, +1. So I'm talking about this point right here on my slope field. And so what am I putting in? Well, again, I really only have to put in my x. So if I put in my x here, which is 0, then the slope is going to be 1. And so at this point, then I'm going to draw a line that's a 45-degree angle on that point. So oftentimes you find patterns in the process of testing points. So you can find a pattern, then you don't have to necessarily test each point. You can just kind of calculate that value. All right, so let's test another value. Let's try -2. So if we're doing -2, 0, I'm over here at -2, 0. When I put in my x, then I'm going to get -2, +1. So that's going to give me a slope of -1. So then at 2, at a 45-degree angle, I'm going to draw me a little tangent line that has a -1 slope. Now, if you look at this particular equation is all dependent on the x. Notice there's no y value on this side. That means the x's are really determining what's going on with this behavior. So I should be able to determine some patterns. For instance, what if I pick 0, 0? Well, when I put a 0 in for the x, I still get a slope of 1. What happens if I put and use 0, 3? Well, I'm still putting a 0 in for x, so I'm still going to get a slope of 1. So I can see that this pattern is happening right here at my vertical axis. And so all of those are roughly a line of 1. Well, then what's going to happen here? What if I pick the point -1, 1? Well, I'm still just putting the x of -1 in here. So -1 and 1 is going to give me another horizontal tangent line. And that's going to be true for all x's that I put in here. So I can tell that I have a pattern where everything in this vertical line is going to have a horizontal tangent line. So what do you think is going to be true about this? They're all going to have a -1 slope because, again, this differential equation is only using the x's to determine the values. So what's going to happen if I go over here to 2, 0, and I put my 2 in here, I get 2 plus 1, so I get a little bit steeper line than this one that has a 45-degree angle on it, and it should be true and the same for all of these. And then if let's go over to this one and I put the 3 in. So when I get 3 here, I get 4. So that's even steeper, but still not a vertical line. When would I have a vertical line? If the slope was undefined, and if it's undefined, we're just not going to write a vertical line at all. We're going to leave it blank. All right, so what's happening over here if I go over to 1 to -3? So I put my -3 in here. And then I'm going to, for my x, so 1, 2, 3, so I put my -3 in here. -3 and 1 is -2. So I'm going to have something a little bit steeper than 45 degrees. Okay, so hopefully you can kind of see the pattern here. And so if I'm thinking about what I know about this graph, I know that the equation had to have originally been quadratic so that when I took the derivative, I got linear. And we performed the integration here to get us back to that quadratic. So I'm hoping then that you can kind of see, if we look and follow these tangent lines, we can definitely see quadratic behavior happening. And we have that little horizontal tangent line right there. So this is what the slope field does. It gives us a picture that looks like the general solution, and the general solution is that quadratic right there. But I could say, for example, if I were given the point -1, 1, that could be an initial condition. And so I could go to my graph and say -1, 1, and I have this point right here. I can use the slope field to help me sketch that in. So it could be kind of going like this and following the slope field around there. It could be going and following the slope field out around there. And so I can kind of see that quadratic behavior at a particular point on the graph. Okay, remember general solutions have infinite numbers of points, but a specific particular solution has the definite points, so you can kind of see the graph. So we can use those slope field lines to help us figure that out. If we're given a point, right, we're given a point, then we're going to put it into the graph and sketch a particular solution. Okay, so just a reminder, table is for your use. Again, I think if it's a complicated one, I probably would use a table. But if it's not complicated like this one, then you can do the math in your head and figure out what your tangent lines are going to look like. Remember that when you're solving, the picture is going to look like the general solution, right, with our plus c. If we have a point, we're going to plot it on the slope field and sketch the particular solution, letting the tangent lines guide the graph as we go. All right, so let's look at the next one. So this one is a little more involved. We have a differential equation or slope generator of x plus y. So we are definitely going to look for patterns. And so as we kind of do that, let's kind of plot some points and see if we can come up with some patterns here. So let's say I start with the point 0, 0. So I'm starting with this point right here. So if I put a 0 in here and I put a 0 in here, 0 plus 0 means my slope is going to be 0. So that means I'm going to have this, I think you can see this, okay? Horizontal tangent line right there, okay? So then as I'm thinking about this, what would have to be true for x and y to be added together, but that's going to produce a slope of 0? That's going to happen when one is positive and one is negative. So if I go over -1 but up +2, I'm going to have a horizontal tangent line. If I go over -2 but go up +2, I'm going to have a horizontal tangent line. If I go over 1 and down 1, so again, horizontal tangent line. I go over 2, down 2, horizontal tangent line. So once I recognize that pattern, I know where all of those horizontal tangent lines are. All right, so what if I do the point 0, 1? So I'm talking about point 0 and this 1 right here. So if I put in a 0 for x and a 1 for y, 0 plus 1 is going to give me a slope of 1. That means a positive, roughly 90-degree angle with a positive slope right here. Okay, so when else might we have a slope of 1? Well, if we went, let's say, over 1, but went up to our point right here, we can follow that pattern down, down, and down. All right, so we're definitely want to look for patterns if we have a very big field, because there's probably some patterns that are going to repeat. And that's going to help us. And again, I didn't really use my table much there, but it's something to think about. Something else to think about, if you have a vertical, if you have a vertical line, right, then that has an undefined slope. So if you see places on here that are left blank, then that might mean that they have a vertical slope. We don't usually draw the vertical line for vertical slope, we just leave it blank. And that might mean that the graph of that original equation or that general solution equation might be experiencing some vertical asymptotes or some asymptotic behavior. So watch for your undefined places. The other thing I want to caution you about is if you have a horizontal tangent line right here, sometimes when you have ones that line up on the x-axis, it's kind of hard to see because it can blend in with the axis. So be really careful and make sure you're always double checking the horizontal tangent line if it's on the x-axis, and make sure you know if it's there or not, because if you just cursory glance over it, you might actually miss it because it could blend in with the actual horizontal tangent line. I drew mine a little bit above, but if they were right on the line, you can see how that might be a little difficult to do. So we are not going to finish this one. For time. All right, I want to have time to get to the FRQ questions at the back. Okay, so let's look at this one, which is loosely taken from a actual AP question. So calculator drawn shown fields for the differential equations dy dx equals xy. So that means this is my differential equation or my slope generator, and it's shown in the figure below. So those lines are a result of the slope field. The solution curve passes through the point 0, 1, so that's 0, 1 right there, and that's shown in that graph. Okay, so now I want you to sketch a solution curve that's going to go through the point 0, 2. All right, so I go to my graph, I go 0, up 1, 2, and I put a dot for that point, and then I'm going to use my lines on my tangent one to graph it. So it's going to look maybe something like this. So that one was my A. All right, well, what now? I'm asking you to sketch a graph that goes to the point 0, 1. So I have 0, 1. Oh, that one's right here. Sorry, I have 0, negative 1. So 0, negative 1. So there's my point. Can you see from that picture which way that graph is going to open? Is it going to open up or is it going to open down? And hopefully you can see that it's going to open down and maybe curve something like that. So that would be part B. And so the other thing, again, like this one, you can't see the horizontal tangent lines that are on this graph. And there are some here and here and here. And so that's what I was saying. You have to be careful when they're generated graphs to make sure and be observant as to whether there's going to be a horizontal tangent line there. And that would be the y value on the x-axis, right? So dy dx would equal 0. All right, so let's move on to example 4. All right, so in this problem, we're going to match each slope field with the equation that the slope field could represent. So remember, when you're looking at this, this is a picture of what the function should look like. All right, picture of what the function should look like. I have all of these slope fields. And then if I look at the equations at the bottom, 7 through 14 are the equations of a function. They're the equations of the function that should be represented in the graph, And the graph is taking the derivatives of the points for the slope generator to be able to create that. So for instance, if I know y equals 0, that's just a horizontal line. If I wanted to think the derivative of that, I could say dy over dx and take the derivative of the left. And then what's the derivative of 0? I'm sorry, I gave you the answer. What's the derivative of 1? It's 0. So I'm looking for a graph that has slope values of 0. And so as I look up here and I look at all of that, I can see this one. Look at all those horizontal lines. That has a slope of 0. So I can come down here and say 7 is D. All right, so what would this look like? Think about this if you're looking at like your hand and you're kind of got this line going like this, right? That's what that is. That's like the parent function of our graph. So it's going like that. And again, if you wanted to, you could say dy over dx. And then when you take the derivative of 1, you subtract down and you're calculating this particular one. So it's just going to be a slope of 1, right? So which of these graphs up above looks like it has a slope of 1? And hopefully that you can see that that's graph H. All right, so what I want you to do now is to pause your video and see if you can match up the rest of the functions, 9 through 14. Pause now. All right, let's see how you did. So you knew this is going to be quadratic. If I took the derivative here, remember I'd end up with 2 times x. So when x is positive, the slope is going to be positive. When x is negative, the slope is going to be negative. So that's why you were looking at C. You had positive slopes and you had negative slopes. All right, moving on through, you should be able to have hopefully identified each of those from that. We have the cubic, which is the little wiggle. Sine started at the origin, where cosine starts at 1. And then down here, what does the absolute value bar of x actually mean? Well, when you have absolute bars around x, that allows this absolute value bar x to be negative. And so what happens is, yes, the absolute value is positive, but I can still put negative numbers in here. So we learned in Algebra 2 that the natural log graph probably doesn't go up quite that fast, probably does maybe something more like that. But then at this point is the 0.10. And that if I'm doing the absolute value bars of that, then if I have this 0.10, then I could have had negative 1. And when I took the absolute value bar, it still would have popped over here. So what that actually does here is it creates y-axis symmetry and a second branch that can be across here, because we know that it can't be on the vertical axis because you can't take the natural log of 0. Okay, so that's one of those guidelines. All right, so let's move on to some more interesting questions on example 5. All right, so as I'm looking at these, notice that these are differential equations, not general original equations. So what would we need to do to get back to the original equation? Hopefully you remember we would need to integrate. So let's look at 15 up here. So I have dy over dx, and that's 1/2 x plus 1. So I can separate my variables because they are differential equations after all. And so when I separate my variables, then I'm going to get dy and then over, well, no, not over, separating it out. So then I'm going to get 1/2 x plus 1, and the dx is going to be on this side. And then when I get to this point, then I can integrate both sides at the same time. So when I integrate dy or go backwards, I get y. And then when I'm integrating this side, I'm going to add 1 to the power of x. That's 1. When I multiply, or that's 2. When I multiply down, it's 1/2 times 1/2. So I get 1/4 x squared. And then when I integrate 1, I get plus x. And then I need my plus c. So what we're looking for here is a quadratic that's had a little bit of vertical dilation applied. And so if I'm looking at this, this is a circular pattern. That's not quadratic. This one, it goes up or down. That's not quadratic. This one goes in and then comes down here. So that's not quadratic, but this one is. So can you see that at x equals -1, we have a slope of 0. So that's a pattern there. And so that means that's probably where my, somewhere having to do with where the vertical, the bottom of, excuse me, the bottom of my quadratic is. So like I could rough sketch in some different ones and go between different lines, and I can have a lot of different possibilities because this is a picture of the general solution. All right, so what your job is to do now, thinking about all the ins and outs and what you might need to help you calculate mentally, or plug in if you want to make a table, you can, is I want you to match graph A, B, C, and D to its appropriate question, 15, 17, 15, 16, 17, or 18. So pause your video and match these things up. How did you do? So I know that when I was looking at this one, if I noticed that my slope is always going to be the y value. And so that made that one easy to pick, which was over here. And on this one, I have my slope is going to be x minus y. So when I'm looking at x minus y and looking at some of those points, then I'm finding my pattern there. And finally, x negative x over y. Well, we know that, for instance, if we're looking at all the points, why do I have an H there? How about, folks, I put my A there and not make my H look, my A look like an H. So I'm looking at what's happening here. So in the first quadrant, all of the slopes would be positive, but then I'm multiplying it by that negative right there, so it actually makes them be negative. But over here, all my slopes would be negative. When I multiply it by the negative right there, these are all going to be positive. So a question like 18, I would probably look at quadrant for quadrant and look for behaviors in each quadrant and see if they match up with the equation that we're given. All right, so let's do a FRQ that has to do with differential equations. This is actually part of an FRQ question on one of the exams, so you can kind of see what it looks like. So first time through, first and second read, first read, orient yourself to the problem, and that's everything A through C. And then 2, on my second read, I would enter the problem, mark it up, pay attention to what it's asking me to do. All right, so if I look at the first one, I see that I have 12 points, so I need to have 12 lines. We're sketching the slope field for a differential equation, so the picture of the slopes of the tangent line. You have a table here you're welcome to use, but it's not required. And so what you're doing is looking for points. Okay, then we move on to part B, and it says describe the points in the plane for which the slopes are positive. So in a problem like that, we need to know what's happening with the x's, what's happening with the y's, and describe those two situations for when the slopes are positive. I don't want a dissertation. I would love for you to use your mathematical notation and be able to do this. And so, you know, I'm looking at maybe some of the points and I'm looking at what conditions. So when this is talking about describing, then I'm looking at what are conditions for X and Y that are going to make this be true. Okay. Then the last part says find the particular solution. So that means we are solving and getting at Y equals. And that's what the differential equation is. It's a slope generator equation. And then we're given initial condition. Sorry about that, my light shut down. All right, and so differential equation here is given this condition. And so that's kind of an important one because we don't want to forget to use it. All right, so go ahead and complete part A, create the slope field for this slope field graph. Pause your video. All right, how did you do? So we know that, for instance, when x equals -1, the equations are always going to produce 1 times whatever they're calculating. You can look for patterns in this equation right here. You can look at calculating and plugging numbers in. For instance, if I looked at the point -1, 0, then I could see that I'm going to get a -1 slope. If I look to the point -1, 1, I can see that I'm going to get a 0 slope. If I looked at different points, that's how I would go about it. So hopefully you're okay with that. So this would be the point -1, 0, which has a slope of -1. And we filled in all of them, but I missed 2 points right here. All right. So probably in grading on an AP exam, you would get 1 point for all of the horizontal lines and 1 point for the rest of it. So probably 2 points total from this particular situation. Remember that when x equals 0, all the slopes are 0, and you can look for just different patterns there. Okay, hopefully everybody's good with that. So now we're going to move on to part B, where it says to describe all points in the xy plane for which the slopes are positive. So the first thing is, what's happening with the y's? What are the y's doing for the slopes to be positive? And hopefully you can see from the picture that the y's are greater than 1, which makes it positive. And then if that's true, what else has to be true? What's going on with the x's for this to be true? And that means the x's can't be equal to 0. So all of the points that are positive in this particular graph have a y value greater than 1, and x can't be 0. And so that's what we're talking about here, the condition. So at y equals 1, the slope is 0. Just applying what we talked about. Okay, moving on to part C. Part C says to find the particular solution, y equals f of x, and you're trying to find y equals, for the given differential equation with the condition f of 0 equals 3. So notice here, this particular point didn't have anything to do with the slope fields. So if you really stumble up here, you can jump down to this part C and you could still do what we've been doing, because what did they give you? They gave you the equation. So you can find the differential equation from there. Same thing is true here. You didn't necessarily have to have the full slope field figured out to be able to see that in order for that to be a positive slope, y has to be greater than 1 and x has to be 0. All right, so part C, you should be able to do this. We have had practice on it. You have taken an AOL on it. You completed that circuit. So find the particular solution. So you're given the differential equation. We have an initial condition. I want to find the particular solution. So to find the particular solution, I have to first remember find the general solution with the plus c. Then I am immediately going to solve for the c, plug it into my equation, and then proceed to the end where I need to find out what is the y equals equation. That's what solving the differential equation for a particular solution is. All right, pause your video and complete this problem. So checking in so far, separated my variables, integrated both sides at the same time. If I do my u sub, then this is my u down here, and du dy is going to equal 1. So I get natural log of u, and on the other side, I add 1 to the 2 to make it 3. I divide down, and it becomes 1/3 x cubed plus c. Now, this is one of those problems. Sometimes students will try to avoid using u sub here because they'll tell me that this is all to the power of 1, so that is dy over y. All right, here's the deal. Yes, you could have figured out the integration and taken the antiderivative and gone to here, and that's true. And I'm okay with that if it's a variable minus a number. I am not okay with that if it's a number minus a variable, because that is definitely going to be a derivative of -1, and you're going to drop the, be more likely to drop that negative and forget it's there. So if it's y minus 1, I'm okay with, if it's cut to the power of 1 like that. But if it's 1 minus y, then I do want to see your u sub, because people just make way too many mistakes at that point in the problem. All right, so now we have our c, so we are going to find our what is the c. So we have our equation with c, so we're going to find out what the c is by plugging in the initial condition. So when I plug in a 0 here, that zeroes out, so I'm left with c on this side. When I plug in over here, I'm doing the natural log, right? So when I plug in over there, what is that going to be? So be careful, because you're plugging in the y, which is 3. So 3 minus 1 is 2. So this is the natural log, and I don't need my absolute value bars, because 2 is not going to miraculously turn into -2. So my equation now is natural log absolute bar of y minus 1 equals 1/3 x cubed, and then we plug in our c plus 2, a natural log of 2. And as I told you before, yes, you can find it at the end, but nope, not for me. I want it done right here. As soon as you find the c equation, then I want you to immediately stop and find the c value and make it into your equation. All right, so keeping in mind, if we're just talking about grading so far, you got 2 points for this, probably a point for all the horizontal tangent lines and 1 for everything else. you got a point for this because you're describing, so that's 3, and remember there's 9 points in total, so the remainder of them are going to come from here. And so we talked before about you're probably going to get a point for separating your variables. You're going to get a point for solving an antiderivative for the left-hand side, the right-hand side, and entertaining the plus c into the equation. And then you're going to get another point when you have an equation with an actual c value. So right now, 1, 2, 3, 4, 5 of the points in this part of it. And so how many altogether? If this is 2 and this is 1, that's 3, then that means there's 6 here. So right now I'm up for 1, 2, 3, 4, 5 points. So I'm going to get the next point for being able to get y by itself, because that's what a differential equation is. Remember, it's y equals, and if you don't solve for y equals, you haven't solved the differential equation. All right, so here's my equation. So to get rid of the natural log, I have to raise this side to e. So I'm going to have absolute value bars y minus 1 equals e to the 1/3 x cubed plus natural log of 2. I'm just changing forms and going from logs to exponents. Then to get rid of the bars, I have to entertain the fact that I have to have a plus or minus for the absolute value bar. So then I'm going to have this side all up there. And then to get y by itself, I'm going to move the 1 over, so I have plus or minus e to the 1/3 x squared plus natural log of 2. Then I'm going to move this over here so it's a plus 1 at the end. But wait, there's more, because I can't leave it as a plus minus. I actually have to use the initial condition to figure out, is it going to be the positive equation or the negative equation? So remember, my initial condition is x value of 0, y value of 3. So if I plug my 0 in here, 0 times anything zeros this out, and e to the 0 power is just 1. And then I have e to this, so e to the natural log base e of 2 is just 2. And so now I have 1 times 2, which is 2, plus 1, which is 3. And that's what I needed my y value to be. So when I'm picking which equation to use, I'm going to pick the positive one, because the positive one already gives me the positive 3 that I need when I test my condition. And so that would be my final one where I'm going to get that last point. So 2, 3, 4, 5, 6, 7, 8, 9 points. I'm on a roll. All right, so this is an example of what an FRQ could possibly look like. You might have to draw in the whole slope field. You might be given a slope field and a point and asked to sketch in where that shape would be. So we'll practice a couple of those to make sure that we're good to go. All right, moving to the last two. So 7 is a tangent line problem. So if we do our first and second read together, we're going to let this function. We have a point 1, 3. It's on the graph of the slope field given by this equation, which means we have dy over dx equal to y over x squared. So notice in this example, they didn't come out and specifically say that's a differential equation, but they said the graph of the slope is given by this. So that's another way that they can tell you that you have a differential equation. So in this one, it says find the slope of the graph at this point. Then in part B, it says write the equation of the tangent line to the graph at x equals 1, and then it says use it to find the approximation. So there's two things that we have to do there. And so we know when we see equation of a tangent line, we need a point and we need the slope. Then when I'm reading part C, I can see that they're giving me the second derivative, and we want to determine if the approximation that we found in part B is greater than or less than the actual. And so if you're given the second derivative and we not want to know greater than or less than, then we need to know something about concavity. All right, and then justify your answer. So that means that you're saying, what's the name of the function? What is it you're doing? Where is it happening at? All right, with that in mind, then let's go ahead and pause our video and work through problem 7. Pause now. All right, let's see how you did. So we need to find the slope. How do we find the slope? We use this slope generator that we have right here. That's the differential equation. So I'm going to evaluate the differential equation at 1, 3 using good notation. And so when I plug it in up here, the y goes on top, which is a 3. The 1 on bottom is squared, which is 1. So the slope is 3, which means I now have my slope for this problem. The point itself was given in the initial condition in the first part of the problem. So that's given. So now I can write my slope equation, y minus y equals slope times x minus x. And our points here are my x and my y. There should be no one in any of my classes that missed writing the equation of a tangent line. Guys, we've been doing this since the first unit. So I need you to get over this. I'm getting people that are giving me crazy slopes and they're putting the numbers in the wrong spot and it doesn't even make any sense, okay? Now, the second part to this is to approximate it. So I used that line and I went ahead and moved my 3 over just to make it easier to calculate. So I put my 1.2 in there. 1.2 minus 1 gives me right here, my 1.2 minus 1, and then I'm going to multiply that by 3. So I get 0.6 plus 3, so I get 3.6. So what that means is, and I need to go back to use my function notation because that's the way the problem is given to me. So then I'm going to say f at 1.2 is approximately, it is an approximation, so use the approximate symbol, 3.6. And so that takes care of part B. Part C, they're giving you the second derivative, and they want to know if it's greater than or less than. So if you're given the second derivative, then you need to know something about concavity, because that concavity is going to help us determine whether it's a greater than or less than, more than, less than, overestimate, underestimate. Whatever the wording is here, that's what I should see in your explanation here. All right, so I'm going to take my second derivative and I'm going to evaluate it at 1, 3. So I'm going to come up here, I'm going to plug in all of my values at 1, 3, and I'm going to get 3 times negative 1 over 1, which makes this a negative. You don't really necessarily need in this particular situation to know the actual value of the number, but you do need to know if it's positive or negative, okay? So now we know that the second derivative is negative. That's what this statement is telling me at this specific point. So remember then, if this is negative, it's concave down, so the tangent line is up here. So we're using a point on the tangent line to approximate the point that's on the curve. The point on the curve is f at 1.2. The approximation is what we found in the last part, which is 3.6. So our conclusion then should be, because the second derivative at the point 1, 3 is less than 0, f of x is concave down at 1, 3, making f of 1.2 approximately 3.6, which is going to be greater than the value at f of 1.2, because remember the value of f of 1.2 is here, the approximation value is up here on the tangent line. So I really encourage you to draw that picture so that you will be okay with that. All right, so let's look at our last one, last problem, and we're finished with this lesson, guys, and basically finished with Unit 7, differential equations. All right, so I am going to ask you to pause your video to go ahead and mark up everything that you can find in all of your parts, A through C, making note of, are there parts where you don't have to have any other information? Could I just jump to part C and work that out because I gosh darn know how to do it? Or do I need to have work and steps from the previous parts of the problem to build up to it? So first step, read everything, all question 8 plus all parts ABC. Go ahead and do the markup and the identification of what you're needing, what you have, all that kind of stuff. And then we'll come back and talk through it a little bit more. But go ahead and pause and do your first 2 reads. Okay, so I am starting at 2010. I have a landfill contained with 1,400 tons of solid waste. It's increasing function, so that might come in handy later, so I marked that. Where W models the total amount of solid waste stored in the landfill. Planners estimate that W will satisfy the differential equation, and so it's giving me a differential equation, dW dt, so differentiating W with respect to time for the next 20 years. W is measured in tons, T is measured in years, so T is tons, W is years, and it told me in this problem at 0 time it's 1,400 tons. So we have this information we can pull out of the problem. T is measured in years from the start of 2010, so that means that time is 0 for 2010. And then that's all my information from the problem itself. So now I'm looking at A says use the tangent line to graph this and approximate. Then B says given the second derivative, determine if your answer in part A is an underestimate or overestimate. So you're going to use the second derivative to do that. So we need to know when it's negative or positive. And then the last one is a particular solution. So I could solve the differential equation and do my initial condition, which is W of 0 equals 1400, or the point 0, 1400. Remember, our points in this particular problem are time and the waste. All right. So as we're working through this problem, we still, even if we got stumped on all of this leading up here, we still could jump down to C and do that without having to know any information from part A and B. So when you're doing the first and second read, make note, are there parts in the FRQ I can do that I know how to do even if I don't know the other values? That becomes a very valuable tool. The second thing I want to point out is we're doing differentiating W with respect to T. So W is actually the dependent variable. And where did we find this variable? It's inside the equation, and we're not quite used to seeing that, so we want to be very mindful of situations that can develop like that. I have seen them give on different FRQs something similar to this, so just being paying attention that this W right here is the dependent variable, not the independent variable. All right, so let's see, what would we do on A? We need to be able to maybe look at the tangent line at some point. We're going to need a point and a slope. So we're given the point W0, which is 1400. That was given right here at the beginning of the problem. And then we need W prime of 0. And so how are we going to find W prime of 0? We're going to find the slope at 0 in the derivative equation. Okay, so that's what this derivative equation is. So I'm going to say dw over dt, and I'm going to evaluate it at the point 0, 1400, being sure that we're getting the 0 and the 1400 in the right spot in the coordinate point. All right, so then I'm going to simply plug into this equation. So I'm going to have 1 over 25. And then what am I going to put in for the w right here when I'm plugging in for the w? Am I going to put the 0 or am I going to put the 1400? Should be the 1400, right? So that's why I kind of always write these points down like this so I can keep track of that. Sometimes you can get lost in a problem and make silly mistakes. So I always kind of go back to where I write out what my points are in the beginning. That's just me. So I'm going to put 1400 minus 300 because that's what's in the equation. And then I'm going to figure this out. So if I do 1400 minus 300, that's going to give me 1100. So I have 1 over 25 times 1100, and 1/25 of 1100 is just going to give me 44. So that's what this evaluation at this point is. So I have my one equal line for this statement, and then my work just proceeded below it. All right, so now I should be able to write my equation of a tangent line. So it's going to be y minus, and remember the dependent variable is 1400. So that's your y, not your x. The slope that we just found, and then x, or in this case t, minus 0. Okay, so t is the variable, 0 is the initial point there, the x value. So then what do I need to do here? I need to figure out what w of 1/4 is. So I have my equation, and I'm going to find w of 1/4. So when I calculate this, I'm going to go ahead and do the math here. So figure out what that w of 1/4 is going to be. All right, so let's kind of think of what's going on here. So if I distribute this through 44 times 0, that's just 0, so it goes away. So I just really need to know 44 of t. And what did we say our t was? It's a fourth. So what is a fourth of 44? That's just going to be 11. So then if I move the negative over here, I have 1400, and then I'm going to add 11 to that. So W of 1/4 is approximately 1,411 tons. So that is a lot. So what does that mean? Let's go back up and talk about right up here at the beginning. Your units is tons per year. So if we're looking at this right here, then this is the rate of change of waste. Okay, so the rate of change of waste, and the units is in tons per year. So then this means that I just added 11 more tons to what I already had just after 3 months. It's just kind of depressing when you think about the amount of trash that we're accumulating there. But that's what that means if you're interpreting the values that we just collected. All right, so let's move on to part B. So on part B, we have a second derivative, and we use the second derivative to determine whether the answer in part A is an underestimate or overestimate. So that means that we need to kind of deal with concavity, being able to tell if it's concave up or concave down based on is the second derivative at the point we're looking at positive or negative. And so in this particular situation, we're going to kind of be looking at what's going on there. So we've already talked about our units here, the rate of change, the ton, and basically we just talked about we put 77 tons of waste in the landfill per year, and then after 3 months we've added 11 tons of waste to that. So always being mindful of your units and how they fit into the problem. All right, so what are we given in B? Well, we're given a second derivative equation that we're trying to find the second derivative. We're given that in this case they gave us time at 1/4, but we're not given the second derivative equation, so we're going to have to find it. So in order to find the second derivative, we're going to have to go up here and find the derivative of the first derivatives to be our second derivative. So on the left-hand side, when we take the derivative of the left-hand side, then we're going to get d squared w over dt squared. So that's differentiating the left side. And the right side, we have a 1/25 we can pull out in front. So now we're just differentiating this part. But this, remember, is the dependent variable. So think implicit differentiation. So if I differentiate here and I differentiate here implicitly, then I'm going to have dw over dt because our variable has changed there, right? So when we differentiate the constant, or this side right here, that 1, we get dw dt, okay? Then this is just, again, implicit differentiation, and so we're deriving with respect to time. So why is this an important thing? Well, because we know we can't leave a second derivative equation in terms of the first, and so we don't have this right here, but luckily we were given it in the original problem. dw dt equals 1/25 times all of this. So I can come down right here and I can make this substitution. In place of dw dt, I can write 1/25 of capital W minus 300. So after I finish plugging in my equation right here, then what do I need to know? Over or underestimate means I need to know if the second derivative is positive or negative. So I'm just going to kind of go up here. So I'm going to find d squared w over dt squared at the point 0, 1400. When I plug that in, I can tell that that's going to be greater than 0, which means it's concave up and my tangent line is down here below. So I should be able to write my conclusion. And so because, however you want to say it, because W is concave up, then that makes concave up. And where did we at? 1/4. So I'm going to say, I thought I was running off the page there, guys. Give me 1 second here. Okay. Makes concave up. This makes, you heard me say that 3 times now. Here we go. Sorry. W of 1/4 being approximately, what did we find that to be? 1,411. And that's where the initial condition is. So W is concave up, making that approximation an overestimate or an underestimate. An underestimate. Right? So that means the estimate's down here on the line, but the point is up here, so you can clearly see that that is below at that point. So I definitely encourage the pictures when you do this to make sure you're saying it correctly. It's really easy to get those backwards if you're not paying attention. All right, finally, you should be able to handle C by yourself. It's a particular solution, and we are given the differential equation, the slope generator, if you will, and an initial condition of 0, 1400, so 0, 1400. They re-gave us the initial condition here. Sometimes they don't, and you have to be really mindful when you're reading and marking up your problem that you make some sort of a notice of it so you don't accidentally forget it in case they don't restate it in the problem. All right, so go ahead and pause your video one last time and find the particular solution. All right, let's see how you did. So we separated our variables. And again, I told you I'm okay if it's W minus the number. If you go straight to here, if it's anything else, then I need to see a U sub. And your U sub in this case would have been W minus 300. All right, so if I went straight to here, then we differentiated this side. So we get 1 over 25t plus our C. Then the next thing we would do would be find the C by plugging in our initial condition. So our C is a natural log of 1100. Then the C gets plugged back into where the C was in this equation. So now you can see it's natural log of 1100. And then our last step then is just to go ahead and solve for the Y value of the differential equation. So to get rid of my natural log, I raise this side to base E. To get rid of the bars, this side becomes plus or minus with the E. Then I can move the 300 over, so I have plus or minus E to the 125th plus natural log of 1100 plus down here in the bottom plus 300. So now I have to decide which is going to be my case. So I plug in my initial condition, and I can, when I plug in my initial condition to the equation, I can see that I need the positive equation to be able to keep this and get the positive Y value that I'm trying to get. All right, so that's an actual question. This is a real important one to make note of, especially with this dependent variable in here. I have seen several FRQs through the years where they did this, and then students got really confused because they didn't realize it was the dependent variable, so they were plugging y's in for x's, and it just caused all kinds of trouble. So definitely want to make a note of this right here, so you're on the lookout for it when that happens. If we haven't talked about it today, then you might not actually think about it, and we're always thinking, not always, but a big part of the time we have, it's the y on the outside and the independent on the inside. So just make note of that. So this is, you work some actual goodness FRQs today. All right, so be sure that you do your check for understanding worksheet. And also then remember, check on Canvas, and if you go to the teacher video note page, you can get a link for the code for the Desmos practice, and the Desmos practice is like what we did here, where you're going to have different differential slope fields, and you're going to match them to the actual differential equation. So I guess it's more like this, slope field matching the equation. That's good practice because that's probably a skill that's going to pop up on multiple choice questions, and want to make sure that we are good to go. All right, guys, thanks so much. Bye.